Hello, in this video we're going to talk about the concept of a mole. A mole is a very important concept in chemistry. It's what chemists use to count atoms, and it has applications all over chemistry. For example, in chemical reactions, in determining the amount of sample present in a gas, and even in determining the concentration of particles in a solution. So remember from our previous videos that the atomic mass of all atoms in the periodic table is defined relative to carbon-12, in that one atomic mass unit, or U, or AMU, is 1/12 the mass of a carbon-12 atom. This is how the whole system of atomic masses is built. Now we want to extend this to macroscopic weight, to something we can measure, because you can't weigh an individual carbon atom, it's way too small for that, but you can weigh a large amount of carbon atoms. So we define the unit of a mole, abbreviated MOL, as the quantity of substance whose mass in grams is numerically equal to the atomic or molecular mass of a substance. So what this means is best illustrated by a couple examples. So if you have elemental carbon, off the periodic table it says the mass is 12.0107 atomic mass units. So we define the unit of a mole such that 1 mole of carbon is that same number in grams, 12.0107 grams. So 12 grams, 12 atomic mass units, same thing on purpose. The same is true for water. If you add 2 times hydrogen plus oxygen together, you'll get 18.015 atomic mass units. And then for this molecule, a mole of water molecules is 18.015 grams. Same number for both atomic mass units and grams of a mole. From this definition, we can make conversion factors. For elemental carbon, 12.0107 grams is equal to 1 mole. So we can say that, well, 12.0107 grams over 1 mole is a conversion factor we can use, or you can invert it and say moles over grams. And you could use these depending on what the units are that you're working with. Flip this over so that it cancels out the units that you want. Same thing for water. 18.015 grams of water is equal to 1 mole, and so you can make conversion factors either with the grams on the top or the moles on the top, depending on whether you're converting from moles to grams or from grams to moles. So given that, we can do a quick calculation. How many moles of water are in 52.3 grams of water? So you always start with the number you're starting with, in this case 52.3 grams. Now we want to convert this from grams to moles. So that means we need to put the quantity of grams on the bottom. In this case, this is the molar mass on the bottom. And then that's equal to 1 mole of water. So you can put the 1 mole of water on the top. And then this is equal to 2.9031. But we have 2 sig figs, so that makes it 2.90 moles of water. So now we can convert from grams to moles. Excellent. What we want to do now is to be able to convert from moles to number of atoms, or number of molecules. We defined a mole so that however many carbon atoms make up 12.0107 grams, that is a mole of carbon atoms, that number of atoms. So experimentally, we've determined what that is, and it turns out to be 6.02214, and we know more digits past that, but I rounded it, times 10 to the 23rd atoms, molecules, or whatever else you're counting. This is a ridiculously large number. We call this Avogadros number after the Italian scientist Amedeo Avogadro, who proposed the experiments that were then used later to determine this number. Okay, so given this, we can see that 1 mole of carbon atoms, which is 12.0107 grams, contains 6.02214 times 10 to the 23rd carbon atoms. That's how many carbon atoms are in 1 mole, the quantity that gives us this mass, 12 grams. The same is true for water, except you are now counting molecules. 1 mole of water molecules is 6.022 times 10 to the 23rd water molecules, and that's 18 grams. So I like to say that the mole is a counting unit. And I think of it as similar to the dozen. You can have a dozen eggs, you can have a dozen atoms. You can have a mole of eggs, you can have a mole of atoms. Same idea. Now a mole is much, much larger than a dozen, but it's still used in the same kind of context. If you want to convert from number of eggs to dozens of eggs, you use the fact that 12 eggs makes a dozen eggs. And the same idea holds if you want to convert from quantity of atoms to moles of atoms. Okay, so the molar mass is 1 mole of something, the mass of it, and that's numerically identical to the atomic and molecular mass. Again, reiterating that concept. Now this number is staggeringly large. If you had a mole the unit of moles the animal, it would cover the entire Earth's surface to 80 kilometers deep, which would reach to the edge of space. That is a ridiculously large number of moles. And for some entertainment, feel free to look up the XKCD article that then talks about the moles floating off to form their own planet, and it rivals the size of the moon. It's a ridiculously large number of moles. Which this tells us that atoms are very, very small, if a giant number of atoms is required to make up a mole of atoms. Okay, so now we can make conversion factors out of this. And to switch examples to aluminum, 6.022 times 10 to the 23rd aluminum atoms is equal to 1 mole of aluminum. Now this is the same for all elements. Just like a dozen eggs is the same number of eggs as a dozen turkeys, the same number as a dozen people, it's all 12. So the same is true for when you're counting by moles, it's 6.022 times 10 to the 23rd particles or whatever in a mole. Now if you want to go from grams of something to moles, that's different for every element, every molecule. Just like the mass of a dozen people is different than the mass of a dozen eggs, the mass of a mole of one element is different than the mass of a mole of another element. Okay, so now we have the pieces we need to be able to convert from mass of an element to number of moles of an element, and then from there to the number of atoms of an element, and then we can go back the other way. So let's use an example. We're going to use chlorine. Say we're starting with 10 grams of chlorine. Okay, in this case the molar mass is 35.45 grams per mole, and Avogadro's number is always 6.022 times 10 to the 23rd inverse moles. So the units here, inverse moles, what it really means is it means stuff per mole. So atoms per mole, molecules per mole, things like that. Okay, so if we have 10 grams of chlorine, and say the question is, convert 10 grams of chlorine to number of atoms of chlorine, or how many atoms are present in 10 grams of chlorine. Well, first you have to convert to moles. So you're going to use the molar mass for this purpose, and you need to arrange it such that the grams part of the molar mass is on the bottom. And the way we write this, 35.45 grams slash moles, implies that the G goes with the number. So 35.45 grams are on the bottom, 1 mole is on the top, great. Then you hit equals, and okay, you have 0.28 moles of chlorine, 2 sig figs. And then on the top of the screen I highlighted what step we just did in the conceptual diagram. Okay, so now we want to convert to the number of atoms of chlorine, and so for that we use Avogadro's number. We need to arrange it so that the moles are on the bottom, and then this means that the 6.022 times 10 to the 23rd goes to the top. Now we can hit equals, 1.7 times 10 to the 23rd atoms of chlorine. Sorry, I ran out of space there. And then on the top I showed what step we just did in the conceptual diagram. Okay, so this would answer the question, how many atoms of chlorine are present in 10 grams? Now let's ask the opposite, or the reverse question. What mass of chlorine is present in 1.7 times 10 to the 23rd atoms? Or probably more realistically, I'd say, what is the mass of 1.7 times 10 to the 23rd atoms of chlorine? Now we do the same steps, just the other direction. So we'll need to go from atoms to moles, and the conversion for that is Avogadro's number. Now we need to put atoms on the bottom and moles on the top, and we want to cross out the unit atoms and leave us with moles. That's equal to 0.282 moles, and here's the step on the conceptual diagram at the top. Now notice, hey look, 0.282, that's the same thing, because we converted all the way to the right, and then now we've gone back to the middle again. We should have the same number. Okay, now let's finish this off, figure out what the mass of 0.282 moles of chlorine is. And you'll use the molar mass for this. Now you need to arrange it so that the grams are on the top. And then that's equal to 10 grams of chlorine. Now we've done the last step on the conceptual diagram, and we're right back where we started, to 10 grams of chlorine. So the big outcome here is when you're using these conversion factors, let the units be your guide. If you start with grams on the top, make sure you use the number so that grams are on the bottom. This is true for all dimensional analysis ever. This is just another application of it. Now we can do an example and see how many hydrogen atoms are present in 2 grams of formaldehyde. So I encourage you to pause the video, try this problem yourself, and then restart the video and we'll discuss the answer. So the first part in this problem is we need to find the molar mass of formaldehyde. So to do so, you take the mass of carbon plus 2 times the mass of hydrogen plus the mass of oxygen. So that would look something like this. And you'll get the mass of formaldehyde in atomic mass units or grams per mole, which is the one we want. So the next step in the problem is to write down the number you're starting with, grams of formaldehyde. And now we need to convert from grams to moles, and then we can go from there to number of atoms. So we're going to use the molar mass. We want to put the grams on the bottom and then the mole on top. So this way we cancel out the grams. And then now we need to convert to atoms of formaldehyde. So we're going to put moles on the bottom and Avogadro's number on the top so that we can cross out the moles and we're left with molecules in this case. And then that's equal to 4.01 times 10 to the 22 molecules. But we're not quite done because we calculated molecules of formaldehyde, but there's 2 hydrogen atoms in each molecule. So we ultimately need to multiply by 2. 2 hydrogen atoms in each molecule. So now molecules cancel out, you're left with atoms, and this is 8.02 times 10 to the 22 hydrogen atoms in 2 grams of formaldehyde. And with that, we've learned what we need to know about moles. It's a relatively simple concept, but one that we use all the time, so make sure that you do what you have to do in order to learn this really well now, and it's going to save you some trouble later. Alright, thanks for your attention.